So now what happens if we want to find the element quicker? That's where binary search comes into play. One of the most famous algorithms in computer science and insanely efficient as well. So similar to linear search, the inputs to this algorithm are a sorted array A and our key K. So we're going to check, is this key within our array? And that's our output. True if it's in A, false otherwise. Here's our algorithm. Quite a bit longer than linear search. So first we check, are our pointers out of whack? If so, return false. Otherwise, we're going to have this variable mid, which is the midpoint of our indices. So we're just going to look right in the middle of our array. So we'll have a pointer at the midpoint. If we're pointing to a value that's equal to a key, then we found our key, so we should return true. Otherwise, if we're pointing to something less than k, we're going to binary search on the right side of the array. So the key thing here is now the array is sorted. So it's not quite the same as linear search. Now the input has to be a sorted array. So we're going to search on the right side of that midpoint if we're pointing to an element that's less than our key, right? Because if it's sorted, the key must be to the right of it. And similarly, if it's not less than k, that means the key should be on the left side of our array, so we're just going to recursively search the left-hand side of it. So that's the pseudocode of the algorithm. As always, we'll walk through an example. But the runtime of this is, well, in the case that we, don't return false here, or we don't return true after just some small comparisons, most of the time we'll enter here. And we recursively call binary search, but now the input size has halved because the mid is our midpoint and we're only taking half of the array here. So that's where this t of n over 2 term comes in. And then all other operations before it take constant time. And if we solve for this, as we did in our recurrence relations example video, that takes O of log n time, which is much, much better than O of n time, which is what linear search takes. Let's do an example. So this is our array. It's in sorted order, and our key is 7. That is the term we're trying to look for. So I'm going to abbreviate binary search as BS. So we're going to call BS on the array from indices 0 to 6, basically all indices, and we're looking for k. So let's scroll up here. Is low greater than high? No, 0 is not greater than 6. So then we need this variable mid. So mid is going to be equal to the floor of 0 plus 6 over 2. That's going to be equal to 3. All right. So then we want to check, is A of mid equal to k? A of mid is 14, and that's not equal to k. And it's not less than k either, so we return binary search on the left side of the array. So this returns binary search. Actually, let me just write out what we just said. So A of mid is equal to 14, which is greater than 7, which is equal to our key. So that tells us we have to do binary search on A from low, which is 0, up to mid minus 1, which is 2, and keep our key, which is 7. Right? So this returns this. So now we have to figure out what this binary search thing is. So let's try to evaluate that. Binary search, 0 to 2, comma 7. So we check, is low greater than high? It's not. 0 is not greater than 2. So mid is equal to the floor of low plus high over 1, or over 2. 0 plus 2 over 2. That's equal to 1. And then we want to compare A of mid to our key. So A of mid is equal to 3. and that's less than 7, which is equal to our key. So if we scroll back up here, we do not hit this first if condition, but we do hit the second condition. So we do binary search on mid plus 1 to high. So this will lead us to binary search. Mid is mid plus 1 to high, so 2 to 2. Did I have that here? Yeah, mid plus 1 to high. And then we keep our key. All right, so again, this returns this. So we can see that, there's some sort of triangulation. We go from here to here, all the way over to here. So it's simplifying down. So now let's try solving for this. BS of A of 2 to 2, comma 7. Well, let's check. Is low greater than high? It's not. Mid is equal to floor of low plus high divided by 2, which is equal to 2. Now let's solve for A of mid. So A of mid is equal to 7. And that indeed is equal to 7, which is our key. So if we scroll up, if we hit that case, then we return true. So this returns true. And that's what we expected to return, because 7 is contained in our array, and that's the thing we're trying to search for. Good. So now before we finish this, let's just consider what happens if our key was 8 instead. Well, okay, we would search through this here for 8. We would look for mid, which would be at 14. So 14 is greater than 8, so we would have to explore this subarray here. So then we would find our new mid, which is 3, and 8 is greater than 3, so we would have to explore the right subarray, which is this. And then we would get 7, we would look here, and that's not equal to 8. So we would explore the right subarray. So we have, this is binary search on 2 to 2. This is what we did right here. But if k is equal to 8, then we would not hit this. We would actually hit this thing right here, right? Because A of mid is 7 and key is 8. So then we would return binary search on A of 3, because mid is 2, to 2, comma 8. And then when we return here, we would see that low is greater than high, so we would return false. So that would be a good exercise to run through the same example, but when the k is equal to 8. So that is binary search, a very, very wonderful algorithm.